All right, so today we're going to be talking about this concept called motion planning, right? And I'm going to start off by actually talking about what motion planning is. By the way, as a reminder, at any time if you have questions, feel free to raise your hand or ask in the chat, and hopefully that will get bubbled up and I'll be able to answer that. So the idea of motion planning is how do we get from A to B, right? If we know a place that we want to be, and I'm being intentionally vague about the definition of place here, but if we have something that we want to, somewhere we want to be or something we want to do, how do we accomplish that, right? What are the steps that we take to do that? So a couple quick definitions. One is configuration, and you guys have touched upon this a little bit earlier when you talked about poses or coordinate transforms, right? You learned a little bit about the position and orientation of a robot, right? That's exactly what a configuration is for us. It's basically just the physical, how you orient your robot or how your robot is oriented relative to the world, right? And the configuration is what determines whether the robot is in conflict with anything in the world. So you could have configurations, certain positions and orientations that are colliding with obstacles, for example, right? And you could also have configurations that are not colliding with obstacles. Motion planning, right? Oh yeah, so just as a heads up, for all of our problems, for real world problems, this is X, Y, and heading. For the immediate future, we're going to talk about X, Y. For some things, we can include X, Y, and heading as sort of a special, or as a generalized case of X and Y. For some things, it's a little bit more complicated, but the basic case we're going to build up from just basically just trying to find a physical path. Oh yeah, heading, by the way, is the direction that you're facing. So yeah, thank you. That was a term that I had not defined. So we then want to find so we define this thing called free space, which is all of the configurations, like I just described, that are not colliding with some obstacle. And the motion planning problem, or at least the path planning problem, can be stated as we want to find a sequence of configurations called a path that goes through from our initial configuration to some target final configuration. Notably, that target final configuration could be a single point that you want to be at. It could be a region that you want to end in, or anything like that, right? It's sort of open-ended what your final configuration is. And you just want to get some path through that. Also of note is that if you look in this figure at the bottom, the configuration space is not the same as just like the free space, sorry, is not just the same as positions that are not occupied by an obstacle. So this particular example is with a circular robot, and you'll notice that all of the free space is sort of inset, right? All of the obstacles are expanded, right? And that's because you can't be, we usually talk about the position of the robot and the orientation of the robot relative to some point on the robot. Usually that's the center of the robot. So we can equivalently say either all of our obstacles are expanded and then our robot is just a point, or our robot is a circle and the obstacles are where they are. We tend to just expand our obstacles. That makes handling things a little bit easier because we already have to not collide with them. So that means that we only have one sort of object that we need to, or one set of objects, one set of objects that we need to worry about. So hopefully that makes sense. So this next slide is about something that a lot of you may have heard of before. If you haven't, that's fine. But it does come up a little bit occasionally in some of the CS classes, I think. So it's the idea of search-based planning, and that's it's an entire family of algorithms. Some of the most common are breadth-first search, depth-first search, Dijkstra's is another one, and A-star. And the idea is that you make some grid of points, and each point is some possible robot state. And then we make connections between points where we can travel directly from one point to another, and we kill off any points that go through obstacles or any edges that go through obstacles, right? And this gives us a structure that CS majors like to call a graph, right? It might not look like what a graph looks like from I don't know, from algebra, right? Where you have a function that you're graphing. It's not that kind of graph, but it is a graph it's called a graph in a certain sense. So if I use the term graph, I will most often be referring to some structure with a bunch of nodes and a bunch of edges. For reference, actually, state machines, like you learned about last week, are also a type of graph. So do with that as you will if you want. That is a useful mental model to have. So yeah, before I go on with that, are there any questions about this? Because this is not actually how we do this search, but about how we define it. Hopefully not. Looks like no. All right. So the way that we actually search through this is, well, it's an iterative process. So I've got this GIF that shows what's happening in a search-based planner. But essentially, we are iteratively expanding, right, and changing basically where, like, the set of nodes that we have searched over. So we start with our initial node, right, and then we find all of the nodes that are adjacent to that, right? All the nodes that we could travel to from that start position or that start configuration. Then we find all the nodes. We go through each of the nodes in that and find all of the nodes that they could travel to, and each of the nodes that they could travel to, and each of the nodes that they could travel to, and so on until we find a node that's our goal. And once we find a node that's our goal, we can essentially just trace back our steps through which ones we expanded in which order. So this is, it sounds like it was what I said was sort of a prescriptive thing, but there are still a couple of key questions, right? Number one, well, really the only question actually, when you think about it, is which order do we actually pull these nodes in? What ordering do we use to pick which ones we explore in, right? And you can imagine that there exists an ordering of nodes that's like perfect. For some way of choosing your nodes, right, you will just, like if you had the perfect way of choosing this, right, you would just step one step at a time, that's the phrasing, along your optimal path, right, around the shortest path. And you would get there without expanding any nodes that you don't need to look at. We can't actually do that for all problems, but a lot of the techniques around this revolve around doing better ways to approximate that, right? So yeah, this general structure of algorithm can apply to can be applied in many different ways. So yeah, like I said, which node do we remove? So the idea of depth first search, sorry, I originally planned to have a couple of pictures here. I do not. The idea of depth first search is that you essentially use something called a stack. And let me see if I can actually make that a little bit more. Okay, anyway, the idea of depth first search is that you're going as far as you can along a particular path before you run out of information, right? So what this stack means is that when you explore or when you have a new node that's adjacent to some node that you just explored, you're gonna use the most recent node first, right? So okay, here we go. I've got a nice little GIF that I should have copy pasted onto my slides. I apologize about this. Let me jump out really quickly. So you can see this node right here, right? Or this picture right here, where we are essentially trying to look all the way, right? And then if we hit something, we just have to backtrack until we have another option, right? So you can see that this sort of explores you can understand why it's called depth first, right? And that's because it's going to go as far as possible, as deep as possible along a certain route. And then once that fails, it's going to backtrack until it gets to somewhere where it's able to make a decision, right? On the opposite extreme is something called breadth first search, which is sort of the opposite. It's basically going to be expanding in a circle, right, outwards from, okay, here's the thing that I actually wanted to use. Here we go. So it's expanding it as a circle out from the original point. And let me actually give you what that looks like. Sorry, I lost everything there. So I've got this demo up. Sorry, I had forgotten to pull this up earlier, and so I was sort of panicking. So what this looks like, if you actually run a breadth-first search, let's not allow diagonal movement for now, is this, right? You see it sort of expanding out, right? Until it eventually finds a path to the goal. Right. So hopefully that makes sense. Unfortunately, this site does not have a depth-first search visualization. That's because depth-first search is a pretty terrible way of actually searching for most of these problems, so you don't often see it used in practice. Anyway, there's another type, though, another type of algorithm, or another variant of this, and that's called Dijkstra's algorithm, right? And this uses a priority queue for the frontier list. So what is a priority queue? Well, it's something that essentially will let the first thing that you pull out of your queue, so the next node that you explore, is the one that is the lowest cost. And well, how do we define cost? We can define this as the basically the length of the path that it actually takes to get from the initial node to that point. So, or alternatively, the shortest path back to the start. And what this looks like, I've got my little visualizer now, so this should be a little bit smoother. Let's look at Dijkstra's, right? We're going to not allow diagonal again. Well, it's actually almost exactly the same as the breadth-first search, right? It doesn't actually give us anything. And if you allow diagonal, it will, because we're sort of looking at things like a circle, right, at this point, it will allow you to take slightly different routes. But in general, once you, in general, it is doing the same thing, where it expands outward at a sort of fixed rate. This isn't ideal, right? And to show you why, let me see if I can move this out into the middle, right? And let's see what I can do here. Let's just shield this like this, right? So actually, let's not do that. Let's leave it whole open. So we know that most likely speaking, the best places to look for paths, right, are going to be through, like, in the direction that's closest to the goal, right? It's not likely, statistically speaking, that we're going to have to go all the way over to the top right corner before we go over to this. But Dijkstra's and breadth-first search, those algorithms both sort of don't take that into account, right? They just expand without discriminating about where the goal is. So how do we fix that? The idea for how you fix that is actually why I brought up Dijkstra's at all, right? Because I showed that Dijkstra's, again, as I said, doesn't really have that much of an improvement over breadth-first search, right? It's just doing this really slow expandy thing where it looks for all of the nodes. It basically brute forces all the paths within a radius of the start, right? And it'll eventually get there, but it's stupidly slow. So, I'll wait for this to finish. So to actually improve this, we can use something called A star, right? And the idea of A star is that, okay, you have your distance, you have as your priority queue cost, right? Remember, Dijkstra's used this priority queue to take into account the cost of each of your nodes. And it turns out that if you take that and you actually say, okay, in addition to prioritizing costs with the lowest path, nodes with the lowest cost path back to the start, we're also going to prioritize nodes that are close to the goal, right? And we do this by having some heuristic, which is just a fancy word for guess, at how long it's going to take to get from this node back to the goal, right? Or over to the goal. The most common heuristic is just going to be distance to goal, right? And it doesn't actually matter exactly what your heuristic is. There are a couple of rules that you need, though. One is that it has to be consistent. And essentially this means that if you have a path to here and then a path to here, the heuristic value from here to here and plus the heuristic value of here to here has to be less than the heuristic value, less than or equal to the heuristic value of here to here. So it's you can sort of think of that as a triangle, right? Going along one leg of the triangle is always going to be shorter than going along the other two legs, basically combined. And then, so that one's not super difficult to achieve in practice. The other important thing is that it has to be an underestimate of the actual value. So in other words, it can't, it's possible if, like, it's okay that your heuristic says that it will take 50 seconds to get to the goal if your actual goal is 60 seconds, but the other way around isn't okay. It needs to be less. And the reason that distance is an acceptable value for this, right, is that if your distance, well, you're never gonna, if you need to get from point to A to point B, the fastest way is gonna be a straight line, right? And nothing is gonna be better than that. So that's always acceptable. Putting all of this together, what does it actually look like when we use A star? Well, it's a lot more efficient, right? It gets very quickly to this point, right? It flounders a little bit because it's trying to find its way through this sort of maze. But in general, it very quickly converges upon a correct path to the goal, right? And you can see, the more, like, if you are in the very direct case, right, where it can go directly to goal, it will actually just expand those perfect nodes, and it will be pretty much optimal, right? And that's because your heuristic is an exact representation of what your actual distance to goal is. So does anyone have any questions about A star? I'm going to actually leave it open because it's a little bit maybe confusing. It's very possible to be confusing. If it is, you're going to get practice implementing it. The exercises are practicing with A star, right? Yes, so the question is, how does it know to go towards the left bottom side, right? And the answer is that the heuristic that we're using is the distance to goal. So it's going to expand nodes that are closer to the goal first, right? As opposed to Dijkstra's, which if you had, clicking things, so if you had this one and this one, right? These two are the same distance from your start, right? Dijkstra's would expand them both equally, right? Or pretty much, it wouldn't care which one. In this case, because this one is way closer to the goal, it's going to prioritize that first. Somebody else asked, how is it an underestimate? So yeah, I'll try to illustrate this without having an actual whiteboard. But essentially, if I'm here, right? If I'm at this position, then I can go. So my shortest distance, the shortest possible distance, will be like this, right? It'll be a straight line to the goal. However, the actual one will have to go around all of these obstacles and then take a straight line to the goal. So basically, all the fact that it's an underestimate is saying is that, as Varun described it as well, Varun's hi Varun. But if you have any curves in the path that you have to take, right? Any deviations from the straight line path, that's going to take strictly longer, right? So the straight line path is going to be an underestimate of how long it could possibly take to get to the goal. Fun fact, you can sort of see that the better your heuristic is, right? The closer it is to your actual distance, the better your results are going to be, right? Yeah, so are there other types of heuristics and what benefits do they have? I'm actually about to cover that. So the better your heuristic is, right, the quicker you're going to find a path to the goal, right? So the closer to the actual value your heuristic is. And you can do heuristics that do like more complex things. Usually in like a maze solving application, it's not really particularly easy to do a better heuristic. than that, but in more complex settings, certainly, right? There are, like, if your state includes something about the world, right? I'll give you an abstracted example from a class called CS 3600, just because this is the first thing that popped into my mind. So that class has an assignment where you're supposed to write heuristics for a system where in addition to just your position, you also have to care about, it's a Pac-Man game, so you also care about whether the pellets are eaten, right? And in that case, so that I know that's a little bit abstract, and it's probably hard for you guys to imagine what the grid would look like for that. That's because it's like super high dimensional. But in that case, you could use number of pellets remaining as a heuristic, right? Because you're going to have to take more time to eat the remainder of the pellets. That was a super abstract example, and it's probably a little bit confusing. But yes, there are other types of heuristics that you could use. That said, for the pure path planning case, very often, actually, you'll just use this type of heuristic. That's just distance to goal, because that is a very good one. Right. I guess it's worth mentioning that they do have a couple of heuristic options here that are different types of distances to goal. So Manhattan distance is just like sum of differences in x and y. So it's basically if your path looked like this, what would the distance be, right? Whereas Euclidean is just straight line path, right? Chebyshev is I can't remember. It's something weird. There are different types of heuristics that you could use for sure. Anyway, I think we're gonna move on. All right. So that was one type of thing. These grid search algorithms are very powerful for a lot of things. However, they can also have some downsides. One is that you do need to construct a grid in some sense. You need a way of constructing a grid, and you need a way of connecting, like basically figuring out how everything in this world is related, right? Which can be a little bit difficult to do. This also can be somewhat inflexible for certain cases, right? So if you, this can be a little bit inflexible in certain cases. So if you have like a very narrow gap between two obstacles, right, your grid might just not capture that. And so A star might say, okay, there's no path to your goal, right? It might just fail. And by the way, failure is what happens when you run out of new nodes to explore in A star. So there are some problems with it, in short. Those can be addressed with some different types of algorithms, and we're going to take a look at some of them. The first one that I have is one that is very near and dear to my heart. It's called the Rapidly Exploring Random Tree Algorithm. It's actually what RoboCup currently uses for some of our motion planning stuff. We want to replace it for some of them, but we'll get to that a little bit later. But it is actually a very cool algorithm in that it uses randomness to outperform something that might be deterministic, which means no randomness, which is a super weird concept. So in general, the idea is that you are creating a tree, which means sort of a tree is like a graph where it doesn't loop back on itself, right? So it's expanding outwards, right? And you create a tree expanding from the start node S, and you repeatedly sample a random point, right? I've got a visualization over on the right side of this. Sometimes you'll explicitly sample the goal, but we're not going to talk about that right now. You find the closest point in your existing tree to that new point. You try to connect those 2 points. You check if the straight line goes through any obstacles. If it's successful, you add P to the tree. And if it's successful and we're at the goal, then we're done. So what this looks like, right, is that we can repeatedly sample random points. All right, and in this case, oops, sorry. Right, in this case, we're actually going to fail to connect them, right, because that goes through an obstacle. So we just discard that. And we're going to repeatedly connect all these random points, right? And eventually we'll arrive at the goal, right? This seems like a pretty simple algorithm. It actually is a very simple algorithm. It's not that many lines of code. The hardest part of it is actually finding where the nearest vertex or the nearest point in the tree is. Anyway, so it's a very neat algorithm, and it works pretty well for a lot of things. Something of note, it actually works very well for super high dimensional spaces. Well, what is a high dimensional space? That just means when you've got many, many, many variables that you're planning over. As a very much tangential note, it was actually used for a while with very great success in humanoid robotics, right? And in humanoid robotics, you've got your configuration isn't just your position and orientation, right? It's actually the orientation, right, of each of your joints, right? So each of those joints on a humanoid is going to add another dimension. Well, that's a very, very complex space. And these trees are able to very, very rapidly explore, hence the name, these very large high-dimensional state spaces, which is a very neat thing. It tends to be, and they can do it very quickly too, which is very cool. Whereas doing that would be sort of intractable if you were trying to create a 100-dimensional grid. You can't really do that. You're just going to run out of memory. So they work by something. The reason that they work very well is something called Voronoi bias, which is a big fancy word for saying you're more likely to explore outwards than inwards, right? So if you have this tree and you look at each of the points in your entire sort of state, your entire configuration space, right? There are going to be some points that are very close to there are going to be some points that are close to a lot of your space, or that are the closest point to a lot of your space, and some points that are close to only a small amount of your space, right? Or put differently, all of this space, for example, this is what's called a Voronoi partition or Voronoi diagram, and all of this space that, can I point the mouse pointer? Yes, I can. So all of this space right here, right, is going to be closest to this point, right? A point that's like right here in the actual tree. And that means that if you select a point, you're much more likely for it to be the nearest point to something that's already at the edge of the graph, right? Maybe that's a little bit confusing, but hopefully it sort of makes sense. Basically, you're most likely to try to connect to something that's on the edge, right? Which means that you get biased towards expanding outwards rather than sort of just filling in a big puddle of things in the middle, right? Are there any questions on that? Cool. We'll move on. So RRT does find a path very well, right? And you can, if you run it forever, right? If you run it with more and more iterations, it is guaranteed probabilistically, which basically means it's guaranteed to eventually find a path to the goal if there is one. It can never tell you that there isn't a path to the goal, right? Because there could always be something that it didn't randomly sample. But as you increase the number of iterations, it will almost certainly find you some path to the goal. However, that path is guaranteed. If you see anything that says like almost or with probability 1, you can just skip over those words and assume that they say guaranteed, because for all practical purposes in the real world, it is guaranteed. It will never find you a perfect path. It'll never find you the shortest path from A to B. We want to fix this because it would be really nice if we could have these shortest paths. And we can get this really cool algorithm called RRT star out of that. I'm not going to go too in depth about how it works, but essentially what it's doing is, instead of just committing, so the issue with RRT, I'll back up a little bit, is that once it's got this sort of kink, if you see where it bends the path a little bit, right, it's committed to that, right? And anything along this branch of the tree is going to keep having that sort of kink in the path. We want something that is able to, after it's done, right, or while it's running, right, constantly reevaluate something that, oh yeah, so somebody asked, is RRT fast enough to run multiple times and take the shortest path? In theory, you could do this, yeah. And that's actually a valuable strategy for trying to get around obstacles in, like, if you're trying to find whether this is the best or this way is the best. RRT won't necessarily tell you which way is the best, but if you run RRT many times, you can find whether this is shorter than the path given from around here, right? From going, basically whether you go left or right of the obstacle. That said, yes, Jason is correct. It is usually better, especially if you have something called like RRT star, to just run one longer iteration. So jumping back into RRT star, right? We want to be able to reevaluate these decisions that we made previously about taking a kink in the road, essentially. So what do? Well, let's walk through a iteration of RRT star. We're going to sample a point, right? We're going to look around that point in a certain sort of ball or radius, right? And we're going to, instead of trying to connect to only one point, only the nearest point, like we do in regular RRT, we're going to try to connect to every point in that, right? And then we're going to pick the shortest, pick the nearest, all that. Keep messing this up. So then what are we going to do? Well, we're not going to pick the closest point, but we're going to pick the point that has the shortest distance back to goal, right? So we can say, okay, in this case, we'd be looking at this path, right, all the way up to here, and seeing whether or not it's shorter than this path, right, that goes all the way around the obstacle, right, and hits here. And if this one is shorter, it's the one that we're going to pick, right? So we pick that. So far, this doesn't really actually give us more, or very much more, over regular RRT. The key step, though, is that we then rewire the tree. Okay. That's upsetting. I missed a couple of transitions, so we don't actually have rewiring the tree in here, which is very frustrating. Essentially, the idea is that, I apologize for that, is that this transition, right, is still better for, it's still a better way to get to this node, right, than going all the way around, right? So when we have that step where we are evaluating all of the nodes in a certain radius, we would actually change the parent of this node so that instead of getting to there by going through this point, you would get there by going through this point and then taking that transition that we looked at earlier, right? Does that make any sense? Hopefully I didn't totally confuse you by the fact that I forgot a transition in this. Sorry about that. I must have gotten distracted halfway through these slides. Okay, so there are a couple of problems in general, especially if we're not using RRT star, but even if we are using RRT star, there are some difficult challenges, right? Number one is that RRT star isn't going to give us a clean path, right? It's sort of, it's still going to give you the shortest path, right? And it might not be as jagged as our regular RRT, but it's not going to be something that the robots can directly follow. And that's because anything where you have like basically a sharp turn in the road, right? Anything where you have to turn 90 degrees instantaneously or something like that, well, that might be the shortest path, but it's not actually something that the robot can follow. Because our robots all, at least if we want to run them at any velocity, they can't change velocity instantaneously from one direction to the other, right? So we can smooth it over by sort of fitting something called a Bezier curve to it. There are other ways to do this. This is just one that Robocop does, for example. But that is not an ideal scenario. It means that like you aren't necessarily planning the exact path that you'll take. You're planning something that will then be messed with a little bit to get the final path. The other question, which is a even bigger question, is how do we plan velocity? How do we say, okay, I want to, start at 0 velocity, and then I also want to end at 0 velocity, but I want to know what velocity I should be taking somewhere in the middle of that, right? And that's actually a very complicated question. That makes your I mean, if you were trying to plan with that directly, it would make your planning, it at least means that we can't do what we were doing right there, right? So the short answer is that with, specifically, especially with RRTs, right, if we have this smooth path that we sort of smoothed over to make it curvy, right, rather than sharp, we can do a velocity profile over it. I'll talk about what that means in a second. Basically, it's saying we want to find our distance along the path as a function of time, and we want to limit that by constraining the acceleration and things like that. What if an obstacle is moving? And this is the most serious problem with this. We can pretend it's not moving. We can't really do anything else. And the reason for that is that if I go, oh, apparently that's how okay, cool. So if we're looking at this, right, there's no time associated with each of these segments, right? There's only a position, right? And trying to plan with time would make this much more complicated. So we can't really take into account, oh, our obstacle will be at this position at this time, because we don't know what time we're going to be traversing this segment, right? That makes our lives a little bit rough. So, sorry, let me, here we go. So long story short, with RRT-based methods, unless we take some great liberties with how we interpret RRT, we just pretend that the obstacle's not moving and call it a day, right? There are some other things that you could do where instead of just planning over X and Y, you also plan over velocity, but those things tend to get pretty complicated with RRT, and you lose some of the things that make it super fast. So this is, oh good, I did actually add a visual for path smoothing. So the idea of path smoothing is that you're basically just going to take the points that your RRT returns, and those might have, these big jagged spots where you have to change angle very quickly. And you're going to try to make some smooth curve that goes along that very well. Bezier curves work really nicely for this. You might have seen those if you've ever used like Photoshop or anything like that. There are also like different types of splines that work very nicely. There are a lot of different types of curves that you can choose for this. I'm not going to get into why you would choose one or the other. There are reasons, but that's beyond the scope of this presentation. Velocity profiling, I did mention that we're going to talk about this a little bit more, is where you try to constrain your acceleration and your velocity so that you can actually traverse, or you can actually go over this whole path, right? This is a figure from a Robocup paper that we put out, just describing sort of some of our planning algorithms, or this part was describing some of our planning algorithms. And essentially all it does, you can sort of see, is velocity increases as you go through the samples, right? And then it decreases, right? And you can do this by making a forward pass where you sort of say, okay, I can be at this velocity, now I can be at this velocity after this amount of time, now I can be at this velocity after this amount of time, and so on, right? And then you can do the same thing in reverse, right? Okay, at the goal, I want to be at 0 velocity. That means 1 second from the goal, I have to be at 1 meter per second. That means that 2 seconds from the goal, I need to be at, and so on, right? You can just sort of iterate that backwards and forwards. So this actually works pretty well, and this is what Robocup currently uses for most of our planners. It's got some downsides for sure, but it does work. Right. That's going to bring us, the downsides are going to bring us into an entirely new field of motion planning, or an entirely new approach of motion planning called trajectory planning. This field is like, I mean, for reference, this is what Jason is doing his PhD. Well, this is a lot of what Jason is doing for his PhD. This is like a huge area of research, and I can't hope possibly to give all of it, to transfer all of it in like 5 minutes or 10 minutes, but I'm going to try. So the gist of it is that we no longer care just about the position and orientation. We also care about all of our velocities. So this means for most of our robots, x velocity, y velocity, and angular velocity, how fast we're turning, right? And we call these variables, all these things that we need to describe our robot, we call them our state. And we want to find a function that maps time to state, right? So we want to find state, where we should be and how fast we should be moving as a function of time. Ideally, we also want to find the controls, which in robotics cases are often like torques on the joint, right? How much torque you're applying to your wheel to make it accelerate. We want to find the controls that are able to give us this trajectory, right? Yeah, so Somebody said, yay, physics. Yeah, there's a lot of physics that goes into this. You essentially, I'll get into it. I'm not going to try to go all over it on one slide because that would be kind of crazy. So I actually, I totally left in something that I wasn't supposed to leave here. So I've been informed that the RoboNav example here is no longer accurate. The others, and in general, well, so these are some examples of dynamics constraints. I'll back up. One is that, and this is very common, robots can only accelerate a certain amount. That's given by wheel friction, right? Actually, it turns out that all of the teams have that constraint. That's just something that I talk about on RoboCup a lot. So RoboCup, RoboNav, RoboRacing all can't accelerate more than a certain amount, right? And that makes sense. You can't instantly accelerate from 0 velocity to 3 meters per second in 0 seconds. You have some friction limits that keep you from accelerating super fast. RoboRacing also has the constraint that it can't steer more than the maximum curvature, right? So that means that it can't, RoboRacing's robot, because it's got a steering wheel and it's what's called Ackermann drive, right? It can't turn in place. And then RoboNav used to have this constraint. I have been informed that this is no longer the case due to mechanical changes, but it used to have this constraint where you can't accelerate too quickly or the robot tips. Yeah, this used to be a really, really big problem. I have been informed that it is no longer a big problem, so that's good. On the IGBC side of things, RoboNav mechanical people did a good job there. So, sort of a tangential direction is this entire field of optimization, right? So in high school calculus, if you took calculus in high school, I think a lot of you probably did, you probably spent a lot of time trying to find minima of functions, right? Trying to find, where this derivative is 0, and you probably thought that was a massive pain and you probably hated it. Congratulations, you might have asked, when will this ever be useful? Now is the answer. The entirety of robotics is just filled with optimization problems, and you'll see that a lot later. You already saw it a little bit in the machine learning side of things, but it just shows up everywhere. So there are a lot of pieces of software that will optimize some cost function. If you just give it a function, it will try to find the optimum of that, the best possible value of that function, right? So a lot of the time we want the best path. We can apply these optimizers, right? And it turns out that in a weird twist, asking for the best path actually is sort of an easier problem, or at least it's easier to think about than asking for any path that doesn't collide with obstacles, right? And let's be specific. What do we mean by best? Well, the answer is you decide. And the entire field of optimization-based motion planning is sort of predicated on the fact that, like, the hard part, or the thing that you need to tune as an engineer, right? The thing that you need to figure out is what your cost function is. There's a bunch of fancy math. This is basically a fancy LaTeXed up way of showing that we're trying to find the best possible trajectory, the best possible state as a function of time, right? Subject to some dynamics, where those dynamics are like how much we will accelerate if we give a certain torque on the wheels of the robot, right? Nothing too important on this slide. It's all like, this is basically just a big blob of mathematical formalism that you'll probably not use a lot. So there are a couple of concepts here, right? You'll notice in this one, I'll pull up my pointer again, that you've got this integral of L dt, right? And L is going to be this function, this sort of function that you're supposed to decide that defines how much cost a particular state and a particular controls are. So for example, I like to think of this, or I like to explain it a lot of the time in terms of dollars, right? You want to be spending as few dollars as possible to get as good of a result as possible, right? So, for example, in a car, right? Gasoline is your control input is your pedal, right? And pressing down on the pedal is gonna cause you to spend more dollars, right? But you might want to get to your goal quickly, and that might outweigh some of the dollars. This is all a little bit weird and abstract, so I apologize. But L is basically the function that says, okay, if I am applying the pedal this hard and I'm in this state, how many dollars does that cost me per second, right? what rate am I burning through money, right? And again, we want to minimize the dollars that we spend. So yeah, and then this other function down here, dynamics, are basically saying, okay, if I apply this amount of controls, right, at this particular point in time with this particular state, how will my state change? How will my velocities and my position change, right? And this one is not necessarily given to you, but you don't get to decide it as an engineer. You want to find it. You want to, sometimes that is like, that involves data intensive techniques where you're trying to find a regression. Sometimes that's straight up machine learning. That's a lot of, that's a really active field of research right now, right? But you need to find this and make it match the real world. This one is totally fictitious. You make this up, and that's how you tune the performance and the behavior of your motion planner. So yeah, instantaneous cost, that's the rate of dollars per second, right? Total cost, that's the integral, or that's the sum of all of the like instantaneous costs over the whole trajectory. And the dynamics are how the state changes. We're going to talk a lot more about dynamics and all this control stuff next week. In the real world, we just make this a sum, and we, instead of saying like derivative of x with respect to time, we just say the change in x over like 0.1 seconds, right? And that just makes it actually tractable on a real computer, right? Because computers don't operate continuously. We don't have infinite processor speed, so we have to discretize it to essentially pretend that it's the right approach. So there's this other thing called LQR. Definitely not going to go into that, but it's a particular subset of these optimal motion planners that use quadratic costs and linear dynamics. Don't worry about, like, you can see the equations, but other beyond that, don't worry about what it means. It just makes the problem very, very simple. And in fact, there's a lot of literature that basically just builds off of this to extend things from this case to more cases, into the case where you're not constrained by these things. This is just a very, very easy case to solve. A visualization of instantaneous cost is often in the form of cost maps. You'll probably learn about those more on team-specific stuff, but suffice it to say that like close to an obstacle is high cost, far from obstacles, that's low cost. Using high control input or high acceleration, right, that's high cost because you don't want to do that. Yeah, that's all. Another approach to this optimization thing is the brute force method. This is also very similar to what, well, it's what a lot of research does. A lot of, especially the lab that Jason and I work in. So the idea is that you can choose many different controls. You can pretty much just randomly select them, and basically that gives you a way of defining a trajectory, right? And then you can just simulate all of those and figure out what the costs are for them and pick the best one. It's a very simplistic approach, but it also actually tends to be very flexible. And using certain magic new technologies that have come out, aka GPUs, that basically do a lot of things very quickly, you're actually able to do this in a surprisingly tractable way. So that's actually also similar to what Robo Racing does for their motion planner. All right, lots of footnotes here. I'm not actually going to read them out. This is all that I have for today, so I think we're going to break out into discussion sections. Subteam leads, try to discuss things about what motion planners your team uses and try to sort of bring things into that context. Other than that, I've also got a Google Classroom link that I will send out to the subteam leads so that they can disseminate them to the teams, so be on the lookout for that. If you have not pressed the attendance button, let me grab a new one of those, because I think it's been an hour. Other than that, you can, if you have already done your attendance, go to a breakout room. Here we go. I just sent the attendance link, so go to a breakout room. Does anyone else have any other questions, I guess? All right, in that case, see you all in breakout rooms.